with the current voltage characteristics of JFET devices and MOSFETs. Now, we've already talked of the construction of both devices. Both are field effect, so that you need the field at the gate to um, to to control the channel resistance or to moderate the channel conductance. And as an effect of that, due to the field applied field at the gate, you control the flow of charges or you control the current. Okay, so this is why these devices are known as field effect devices or field effect transistors. This is a basic transistor action that you apply the certain gate voltage, and that gate voltage affects the resistance of the electron flow. Um, you might if you go on increasing the reverse bias the junction at the gate, you might pinch off the channel. Okay, so this is the basic transistor action. The flow of electron is controlled by the field effect at the gate. Now this field is applied by usually by the VGS at the gate, which is the supply. Okay, so the circuit symbols for the N channel and P channel JFETs, they are shown in figure 59 over here. You can see that in part A you have an N channel JFET. Okay, part B shows a P channel JFET. The direction of the currents are reversed over here. You can see the source and drain terminals. These are the other way around um, in the N channel because of the direction of current as such. Okay, so the polarities of VDS and the direction of currents are shown in these two symbols. So the ideal current voltage characteristics when the JFET device is biased in the saturation region is described by the given equation. Now you can see that this uh, equation at VGS equals to 0 is nothing but IDSS. Okay, so if the gate to source voltage, if there's no field applied at the gate terminal, source is at the body potential, which is ground. Okay, so this current is IDSS. Okay, small current that flows between the source and the drain. Okay, without VGS. So this current is IDSS. So IDSS is the saturation current when VGS is 0, and VP over here, this parameter is the pinch off voltage. You see, if VGS is set to VP, then your current is 0. Okay, the current is 0, which means the channel has been blocked. Now, if you recall the construction, what we have talked before earlier, now for this construction, you have an N channel device over here, right? The electrons are flowing from source to drain. So what happens is that this is open circuit conditions. In these open circuit conditions, ID is your IDSS, right? As for a small application of VDS, you have a small current IDSS, and this is generally an ohmic in the ohmic region or linear region of ID VDS curve. Now, as you go on increasing VGS, keeping VDS the same, you go on increasing VGS. This is an N-channel MOSFET. So in order to reverse bias the PN diode over here, the PN diode is in this direction, right? This is your PN diode. So PN diode is being formed over here between P and N. So again, this is the direction of the diode. So in order to increase this depletion width, you need to increase VGS. So VGS is negative voltage. So with negative voltage, you reverse bias the region, the depletion width increases. And if you still want to increase the magnitude of the VGS more, which is the negative voltage, then the channel is pinched off. Okay, the channel is pinched off, and the transistor is in off state. There is no current. Okay, so when VGS is equal to VP, this is VP, the pinch off voltage. For an N-channel device, this pinch off voltage is negative. You can see over here. Why it's negative? Because you need to apply a negative gate voltage to reverse bias the PN diode forming at the gate. These both are the gate terminals which are shorted together. These are both the gate terminals at the same potential at minus V2 minus V2, and this the voltage at which the channel is pinched off. This is called the pinch off voltage, and this state you can see that there could be no flow of electrons from source to drain. So you can say the device is off in this condition. Okay. So now naturally for the N-channel device to reverse bias this PN diode at the gate terminal, you need to apply a negative gate voltage. and Vp, the pinch off voltage, is also negative, that is less than 0. Therefore, for this n-channel device in this expression, VGS is negative, Vp is negative, so this ratio is positive. Okay, this ratio is positive for n-channel device. So what it says is, note that the pinch off voltage Vp for an n-channel JFET is negative, and the gate to source voltage is usually negative again. Therefore, this ratio is positive. So, for example, in figure 60, the first part A shows an n-channel JFET IV characteristics. This IDSS is for 0 VGS. Okay, this is the current. Now, you apply the negative gate voltage to reverse bias the gate terminal, and you keep on increasing the magnitude of the negative supply voltage at the gate. A point comes when you reach the pinch off voltage. So when VGS is less than Vp, which is negative again, the transistor turns itself off. Okay, so the current becomes almost 0. Okay, so in the p-channel device, it's the other way around. VGS is positive. Why it's the other way around? You see, what happens is that in a p-channel MOSFET, you don't have this p-doped region. Instead, you have this n-doped regions. Okay, n-doped regions, and the direction of this p-n junction diode is the other way around. It's reversed. So for n-doped gate regions, you need to apply a positive gate voltage. So it has to be positive. Then. If it is positive, then that means since you will be traveling holes, there will be holes traveling between source and drain. Then that means you need to apply a positive voltage, okay, to reverse bias this junction, just like before for n-channel device. So the pinch off in this case will be greater than 0. The pinch off for the p-channel JFET is greater than 0. Once again, this ratio VGS over Vp is positive. So for both n-channel and p-channel JFETs, junction field effect transistors, this ratio is positive. Okay. So since the pinch off voltage for the JFET is positive, the gate to source voltage must be positive. Therefore, the ratio is again positive. So you can see for a p-channel JFET, applying a positive VGS values over here. So VGS is always positive. The pinch off is always positive. Okay, this is the difference. But again, the morphology of the curves and the shapes, the behavior is very similar for p channel and n channel. It's the direction of currents and the polarities that are being changed for drain to source voltages due to reversing of the doping regions. The polarity of the reverse voltage required to pinch off the channel is changed. Uh, it's positive in the p channel, it's negative in the n channel. Okay, similarly for VGS is negative for n channel, positive for p channel, as shown. Otherwise, shown in this figure, as otherwise the saturation region, the behavior of device in saturation region, or in the ohmic region over here, this is the ohmic regions. It's quite the same. Okay, when the transistor is on, it is either in ohmic region or saturation region. But otherwise, if your VGS for p channel is greater than Vp or less than Vp, the transistor is cut off. Okay, not conducting. There's no conduction between drain and source. Okay, now for an n-channel device, the transition occurs from non-sat or ohmic region to saturation region when VDS is greater than VDS-sat. You see over here, this relationship is when the transistor is biased in the saturation region. So you don't see any dependence of ID on the factor VDS. Okay, so the ID is not being dependent on VDS or VSD. Even you are increasing VSD or VDS, the drain to source voltage, the current stays constant. But what happens in practice is that you might have a channel width that is being modulated by VDS, as we have seen before earlier. So the physics is as such. As you go increasing VDS, well, you might you're changing the channel resistance. Okay, and you might not have a flat region like this. You might need to consider forward resistance or not. Okay, so let's talk about this more in detail a bit later. But before that, now what we are interested is, what about this point? Okay, these are the points for the given VGS curves. Now for the given VGS curves, we have this saturation points in JFETs characteristic curves, and what this voltage, this is the overdrive voltage. Okay, so the minimum VGS that you require above the threshold voltage is what determines the transition point. So for an n-channel device, VDS saturation is given by VGS minus VP. Similarly, for p-channel device, the saturation occurs when VSD is greater than VSD sat. So VSD is VP minus VGS. Okay. Now, this example shows how you can use this IV relationship to calculate the drain to source current. What it says is the objective is to calculate ID and VDS set, the transition point in N channel P and JFET. So assume the saturation current is 2 milliamps, which is for VGS equal to 0. Pinch of voltage, it's an N-channel device, so pinch of voltage is negative. As you can see over here, the gate source voltages. The gate source voltages are negative, okay, -1, -2, -3. So pinch of voltage for N-channel device in part A are negative. So pinch off is negative. So calculate the ID and VDS sat for VGS equal to 0, quarter of the pinch of voltage and half of the pinch of voltage. Now, if you use this in saturation, so we are given the saturation current, right? So for VGS equal to 0, you can see it's quite straightforward. For VGS equal to 0, the ID is 2 milliamps, right? No, you don't even need to calculate this. But then for the 1/4 of pinch of voltage, if you substitute VGS by VP by 4, then this is 1 minus 1 over 4, which is 3/4. Then this becomes 9. 3/4 is 9 by 16 IDSS, which is again 2 milliamps. So if you calculate this, this is a little bit larger than 1. This is 9 by 8, which is equal to 1.13. So that's the case over here. This is for VP4, VP by 4. 4 times the pinch of voltage. For the 4 time pinch, since you are applying the gate source voltage, negative gate source voltage is quarter of the pinch off, so the current is being reduced, right? You're reducing the current. I mean, you're moving towards this pinch of voltage, okay? So somewhere in between where pinch of voltage is, you are about 25% of pinch of voltage. The current is expected to decrease because you are decreasing the channel width, right? Or you're increasing the depletion or the reverse biasing of the PN junctions at the gate. So then again, when you apply more negative voltage at the gate, more reverse biasing of PN junction occurs. So in between you have half of VP, okay? Somewhere in between you have half of VP. This is not VD, this is VP. So your current further decreases, okay? So this becomes when this is VP by 2, then this is 1/4 of IDSS. So 1/4 is 4.5 milliamps, okay? This is with VP by 2. So the current is reducing. This is expected. Then for VDS sat, you see VDS sat, these points, this over here or in N-channel device, you see they are the function of VGS. So for each VGS, you have different transition points. So let's find them out. You see this, first of all, over here, you have for VGS equal to 0. So let's use this equation for N-channel device. So for 0 VGS, when there's no gate source voltage, the pinch off voltage is given. That is minus 3.5 volts, which is then it turns out to be 3.5 volts. So this is VGS minus VP for N-channel device, so 3.5 volts. Okay. Then for 1/4 of VP, this point is shifting towards left. Okay. As you are, so for example, you were over here. This is minus 3.5 volts. Then as you increase the negative gate voltage at the gate terminal, this point is going to shift towards left. So on the VDS scale, this is going to shift down. Okay, so you are shifting this towards left. So the voltage is reducing. So that means the transition point, or where the transition occurs between non-sat and sat region, decreases. So for VP by 4 with the negative gate voltage, it still reduces 2.63. Okay, so you substitute this by, so VGS is going to substitute by VP by 4. Okay, this becomes about 3/4 of 3.5. Okay, then you have VP by 2, which becomes half of VP. Okay, so this for VP by 2, this is VP by 2, this is VP, so this is again half of VP, half of VP, half of VP. So that is 1.75 volts. Okay, so you are shifting down. The voltage required is going to shift down. So this example shows that as you increase the pinch of voltage, the current reduces. Which can be shown in this graphs. As you increase the pinch of voltage, the negative gate voltage, which is a certain fraction of pinch of voltage. you're reducing the current, so the current is being reduced over here. That's the first thing to note. And then for the given VGS, for the given VGS that is lower than VGS equal to 0, your saturation points are also shifting. They're also shifting towards left. Okay, so they are reducing in magnitude. That's the idea of this example. So this example illustrates this, basically explains this IV curves for the JFETs. Okay, now one of the comment about this this example is the current capability of JFET can be increased by increasing the value of IDSS, which is again the function of the transistor width, which means it's not it's the transistor width, or call it the channel width. Okay, so channel width. If you increase the channel width, the current handling capability of transistor changes. It increases. Okay, so you can affect this parameter IDSS, which is dependent on the channel width. So now, as in the case of MOSFETs, ID versus VDS characteristic for JFETs, they may have a non-zero slope beyond the saturation point. And this non-zero slope can be described to the following equation. Now you have a modulation parameter lambda. Okay, so if you take the to find this output resistance, now you see the parameter this I over V is in Siemens. So you take the inverse of the slope. This becomes volts by I amperes, which is ohms. So you take the inverse, you take the gradient, you take the derivative, and take the inverse. So that becomes forward resistance for the given VGS. And if you carry this evaluation, you'll find this out if you substitute this over here, this expression, and this expression. You take the inverse of the gradient.